So, now in this session we have to discuss another fundamental concept that is very important even in the board examination also, that is isotopes of the carbon and allotropes of the carbon. So, here we are using two different terms, isotopes and allotropes of the carbon. One can define these two terms very easily, and first of all we have to know the difference between these two words or terms like isotopes and allotropes. Let us move on to isotopes and then we can discuss about allotropes of the carbon. So, now here isotopes of the carbon, here the basic definition of isotopes already we know. What is the isotope? The atoms of the same element which have same atomic number and a different mass number. The atoms of the same element with the same atomic number, different mass number. Such type of atoms are generally called as isotopes, we all of us know. So, best examples for isotopes of carbon are C 6-12, 6-13 and 6-14. So, here what are important characteristics these isotopes can exhibit, that we have to know in detail. So, coming to the characteristics of isotopes, the first important property or characteristic is that is about the physical state of isotopes. So, in general the three isotopes of the carbon are present in the solid physical state. That means, what we can say, isotopes of carbon are generally present in same physical state, that is in the solid form, and second one, they are present in the same physical form. So, here I am using physical state and physical form. What is the difference between the two words, physical state and physical form? So, here the basic difference is physical state is like either solid, liquid or gas, but when it comes to the physical form, the appearance of that particular substance in the nature we can consider. So, when it comes to the isotopes of carbon, all the three isotopes are present in similar physical forms, and about their physical as well as chemical properties we are supposed to discuss. So, in general isotopes of elements generally they will exhibit different physical properties and they will show similar chemical properties. Let me explain why like this. So, I am telling here they will exhibit different physical properties. What is the evidence to that point? Here if you observe the isotopes of carbon, mass numbers are varied. First isotope is 12, second is 13 and third is 14. So, here mass number or atomic mass is being varied, then automatically we can observe some variation in the physical properties of the isotopes. And here if you observe what type of atoms are present or what is the atomic number of all these three isotopes, very good, it is 6 only. So, as per the atomic number, if you write electronic configuration of all these three isotopes, what type of valential configuration we will get, that is very common, or same valential electronic configuration we can obtain for all the three isotopes of the carbon. That means, whenever the element or atom is having same valential electronic configuration, we can say that they will show similar chemical properties. Why? Because the valential electronic configuration will decide the chemical properties of the elements. So, overall if you see the isotopes of carbon, three isotopes we can see 6-12, 6-13 and 6-14, and these are the important characteristic features of the isotopes of the carbon. So, based on this concept, in a very recent board exam, that is March 2020, we have observed one important MCQ type of question under comprehension type. And next move on to the allotropes of the carbon. So, here as we have discussed about isotopes, here first of all we have to know what is meant by allotrope or the phenomena allotropy. Here clearly you can see the existence of an element in same physical state, but in different physical forms. I am repeating again, here the existence of an element in same physical state, but in different physical forms. So, here what or how the existence of these allotropes of carbon we can observe here in detail. So, here I am using two terms again, one is physical state and the second one is physical form. So, best examples of allotropes if I take, there are two categories, one is crystalline allotropic forms and second one is amorphous allotropic forms. So, now here best example for crystalline diamond, graphite, not only these two, we can also observe like Buckminster Fullerenes and nanotubes or graphenes also we can say as crystalline allotropes of the carbon. When it comes to amorphous form of allotropes of the carbon, mainly we can say like a coal or coke or lamp black or gas carbon. So, these are the important types or categories of allotropes of the carbon here. Now, let us move on to the characteristics of the allotropes of the carbon. So, in general these characteristics of allotropes also somewhat very similar to the characteristics of the isotopes, but where these are different when compared to the isotopes we have to see clearly. So, let us see the first property, that is about their physical state. So, if I take either crystalline or amorphous forms of the carbon like allotropes of the carbon, what is the physical state we can observe? The physical state of the carbon is solid only, or diamond, graphite, coal, coke, all these are present in the solid physical state. That is why in the definition itself we are telling these allotropes are present in same physical state. And second property, if I observe different physical forms. So, here already I said physical form in the sense it is the appearance of the substance in the nature. So, if I observe diamond, graphite, fullerenes, all these they are like crystalline forms, but when it comes to the coal, coke or lamp black, all these are amorphous forms, that is nothing but in the powdered form we can observe. So, crystals and powder, the appearance of the substance will be different here, hence we can say they will exist in the different physical forms. And coming to the third property here, that is different physical properties and similar chemical properties. So, these two are very similar to the isotopes of the carbon we can see. Why? Because either it is isotope or allotrope, by using which atoms these are being made in the nature, that is very good. Only by using carbon atoms we can observe the existence of either isotopes or allotropes of the carbon. So, when atoms are similar, we know that in case of isotopes mass number is different, hence the physical properties are different. In a similar way here the arrangement of atoms will be different. I am telling here physical forms are different. So, physical form difference is possible only by the arrangement of atoms. When there is a difference in the arrangement of atoms, we can observe the variation of physical properties. And as it is made from only carbon atoms, we can say or we can conclude like they will show similar chemical properties. So, like this allotropes all together examples and the important characteristic features of allotropes we need to remember. Now, let us move on to the study of three important allotropes of the carbon, that is crystalline allotropes, diamond, graphite and fullerenes. So, these are the three important crystalline allotropic forms of the carbon. So, in detail we have to study one after one. So, about their properties, structural arrangement and their uses. So, here first of all I am taking diamond. So, coming to the hybridization. So, whenever we are going to study in detail about the properties of allotropic forms of the carbon, so there are few important points or properties we need to remember. The first property is about their hybridization, second one is about their shape or structure of the particular allotrope, third property is about the conduction, either it is good conductor or bad conductor of electricity, and the fourth one is the similarity in the chemical properties of these allotropic forms. So, likewise diamond if I take, so here diamond, in case of diamond carbon undergoes sp3 hybridization. In case of diamond carbon undergoes sp3 hybridization. So, we all of us know already whenever carbon undergoes sp3 hybridization, the shape of hybrid orbitals or the arrangement of hybrid orbitals we can say that is tetrahedral. So, I will show you the molecular arrangement here just by taking our models. So, this is tetrahedral arrangement we can observe. So, here imagine this black colored ball is like a carbon atom and these white colored are hydrogens involved in that. So, whenever carbon undergoes sp3 hybridization, we can observe the arrangement of all the 4 hybrid orbitals in the tetrahedral manner. So, like here if I rotate in any direction, the arrangement of the hybrid orbitals will be same like that. So, here the bond is also in the equivalent condition, that means here between these two bonds if I take, it is 1 at 9 degrees, and here between these two bonds also 1 at 9 degrees like that. So, just like the way how methane molecule is formed in this manner. So, the hybridization of carbon if I take, here it is undergoing sp3 hybridization. So, all the carbon atoms here are arranged in the tetrahedral manner, and coming to the conduction property. So, here it is acting like a bad conductor of electricity. Why it is acting like a bad conductor, I will explain later when I am discussing about the graphite. And next fourth one, the fourth chemical property is it forms carbon dioxide gas upon burning. So, how we can conclude this? Why it is forming only carbon dioxide gas upon burning? As we all of us know, these allotropic forms are made up of carbon atoms alone. So, whenever we are burning carbon in the presence of oxygen, we can observe the formation of carbon dioxide gas itself without leaving any residue. So, in a similar way, when we are burning diamond at high temperatures, we can observe the formation of carbon dioxide gas without leaving any residue. And coming to the uses of diamond, it is very much useful in the removal of eye cataract. So, in the eye treatment, surgeons generally they will use the diamond, the sharp edged diamonds in order to remove the cataract of the eye. In addition to this, some other uses also we know, and the best use already we know that it is used as a very good item in the jewelry process. And next move on to the graphite. So, the second allotrope, crystalline allotrope is graphite. So, here hybridization of carbon in the graphite if you say, that is undergoing sp2 hybridization, and whenever carbon undergoes sp2 hybridization, we know that the arrangement of all the 3 hybrid orbitals will be in the trigonal planar form. So, the arrangement is just like this. So, here imagine this is the carbon and these are the hydrogens involved, just the way how ethene molecule before we have discussed. So, like this the 3 hybrid orbitals are formed will be arranged in the trigonal planar form. Okay. So, the bond angle here is 120 degrees between any 2 adjacent bonds. So, in a similar way in the graphite also carbon undergoes sp2 hybridization we are telling. That means, the carbon atoms are arranged in the trigonal planar, that means hybrid orbitals are arranged in the trigonal planar, but here all carbon atoms are linked together to form a hexagonal ring structure, So, we know hexagon, that means how many carbon atoms will be present? 6 carbon atoms with the 6 corners we can observe, and that arrangement if you see, so this is just like a hexagonal ring structure. So, like this different rings will connect together to form one layer of the graphite. So, these are the hexagonal rings we can observe. So, these hexagonal rings are connected together to form the one layer of the graphite. Likewise, layers and layers will be attracted each other with a weak van der Waals force of attraction. Okay, with a weak van der Waals force of attraction. So, hence finally coming to the structure of graphite, what we can conclude is it is having hexagonal ring structure as well as layered structure. Between the layers we can observe the presence of weak van der Waals force of attractions. And then come to the conduction property. Graphite is acting like a good conductor of electricity. Graphite is acting like a good conductor of electricity. Why? Because here compare the property, conduction property between diamond and graphite. So, as I said before, diamond is bad conductor of electricity, but graphite is a good conductor of electricity. Once you move back to the concept, at the beginning of the chapter itself, we have discussed about the excited electronic configuration of the carbon. How many unpaired electrons are present in the excited state of electronic configuration of carbon? We know that it is 4 unpaired electrons. So, now when we are observing carbon is undergoing sp3 hybridization means 4 sp3 hybrid orbitals are produced with the 4 unpaired electrons. So, these 4 unpaired electrons are completely involved in the bond formation with other carbon atoms in the case of diamond. That is why there is no free electron here, hence we can say that diamond cannot conduct electricity. But in the case of graphite, if you observe the structural arrangement, as per the sp2 hybridization, how many hybrid orbitals can be produced by the carbon? Yes, very good, that is only 3 hybrid orbitals with the unpaired electrons. So, here the 4th electron is present in the free condition. So, that 4th electron which is present in the free condition will be migrating from one carbon atom to the other carbon atom within the structural arrangement. So, that the due to the presence of free electron, graphite can act like a good conductor of electricity. So, here the conduction property, if I take the relative comparison, diamond is a bad conductor because there is no presence of free electron, but when it comes to the graphite, it can act like a good conductor due to the presence of free electron. And next, coming to the chemical property, how it will show or what type of product formation is possible when graphite is burning at high temperatures. So, it is very similar to the diamond. The 4th property, if you observe, even graphite also can form only carbon dioxide gas without leaving any residue upon burning process. Why? Because even graphite also made up of only carbon atoms. And then come to the uses. So, the important uses of the graphite, if you observe here, it is one is it can be used as a very good lubricant, and second one is it is useful in the preparation of electrodes in the electrolytic cell. So, here I am telling graphite can be used like a lubricant. So, because of which property of graphite we can use that as a lubricant. Already I said before, the structure of graphite, if you see, it is having hexagonal ring structure as well as layered structure, and here between two layers we can feel or we can observe the presence of weak van der Waals force of attractions. So, whenever the weak van der Waals force of attractions are present between the two layers, we can observe the sliding of layers on one another. So, because of this sliding of layers of graphite, some slippery nature will come for the graphite, that makes the graphite as a very good lubricant. So, what is the reason here how we can use graphite as a lubricant means due to the presence of weak van der Waals force of attractions between the layers of the graphite. And come to the third crystalline allotrope, that is fullerenes. So, in case of fullerenes also, in a very similar way we have to observe the properties like this. The first property is about hybridization of the carbon. So, what is the hybridization of carbon? We can observe that is similar to the graphite, sp2 hybridization. So, all these 3 hybrid orbitals which are produced will be arranged in the trigonal planar manner, but here the overall structural arrangement of the fullerene, if you see, it is somewhat different from diamond as well as graphite. How it can be obtained is, it is totally made up of nearly 60 to 120 carbon atoms. Generally, fullerenes are containing the Buckminster fullerenes, 60 to 120 carbon atoms range we can observe. So, these carbon atoms in general they are formed like 20 hexagonal rings and 12 pentagonal rings. So, altogether each and every Buckminster fullerene is composed of total 32 rings in it. Out of 32 rings, one is hexagon, that is 20 hexagonal rings, and the second type is 12 pentagonal rings. So, it is just very similar to the football like structure, that is why these are also called as buckyballs. These are also called as buckyballs. And conduction property of fullerenes, if you observe. So, the hybridization of carbon, even in the case of fullerenes also, it is sp2 we are telling. So, just like graphite, in the fullerenes also we can see the presence of free electron as it is undergoing sp2 hybridization. So, now you tell me children, so fullerenes can act like good conductors or bad conductors? Very good. So, fullerenes also can act like good conductors as there is a presence of free electron due to sp2 hybridization of carbon atoms. And moreover, at very low temperatures, if you study the conduction property of these fullerenes, they can act like superconductors. At low temperatures, these fullerenes can act like superconductors. And then come to the chemical properties. So, here even fullerenes also upon burning, they can form only CO2, carbon dioxide gas, without leaving any residue. And coming to the uses, it is very much useful in the biomedical field. That means, in the drug delivery technology or gene delivery technology, in the MRI or X-rays, these fullerenes are generally useful nowadays. So, like this, the important properties of crystalline allotropic forms of the carbon we have to study in detail. So, here finally, I am going to ask you one question, just try to answer. So, how can you prove that diamond, graphite and fullerenes, all these three allotropes are only made up of carbon? How can we prove? The best evidence here is the fourth property. So, if you see the fourth property in all the three cases, whenever we are burning these crystalline allotropic forms of the carbon, they are forming only carbon dioxide gas without leaving any residue. That itself indicating these allotropic forms are made up of purely carbon atoms. Students, here I would like to ask you one question. First of all, what is meant by organic chemistry, or why we have to study organic chemistry or compounds of carbon? So, in general, in our day to day life, if you see, it is very important branch of chemistry, as all these carbon compounds are produced by living things or carbon containing compounds we know. So, here why carbon deserves a special branch of chemistry? When that question arises, the most appropriate answer we can give as because of its unique properties. So, when compared with other elements, carbon will show some unique properties. Because of those unique properties, it deserves a special branch of chemistry, as it can form millions of compounds in the nature. So, let us see these unique properties of the carbon. So, out of these properties, the first one is catenation, second one is Tetra Valency of the carbon, third multiple bond formations, and the fourth one is isomerism. So, these are the four important unique properties of carbon we are supposed to discuss in detail, so that we will understand why carbon deserves or why carbon can form millions of compounds in the nature. So, let us move on to the catenation. Simply we can define this catenation property as the self-linking ability of an element. The self-linking ability of an element is called as catenation property. That means, what we can observe during this catenation property is the atoms of the same element will link together to form different lengths of chains. Here best example carbon, as we are discussing, different number of carbon atoms can be linked together to form different lengths of the carbon chain we can see. So, here I am taking 6 carbons chain. So, not only these 6 carbons, we can observe the carbon chain with 5 carbons, 10 carbons or 100 carbons or whatever it may be. So, like that, as the number of carbon atoms bonded together may be varied, it can give the different composition in the organic compounds. That is one of the reasons for the existence of millions of compounds in the nature. And the nature of carbon chain also will be somewhat different. Here it is a very straight carbon chain, but here I have represented the second one is branched chain, and the third representation with the 6 carbons, that is a closed chain or cyclic ring structure. So, whatever it may be the nature of the carbon chain, it can form different varieties of carbon chains by the property of catenation. Self-linking ability of carbon is nothing but catenation property. And the next one is Tetra Valency. So, from the beginning of the chapter, we know that how many valence electrons are there for carbon? 4 valence electrons are there. So, as 4 valence electrons, and these 4 valence electrons are present in unpaired condition in the excited electronic configuration, it can form 4 different bonds with the different elements. That is why the tetra valency of the carbon is 4 we can say. Because of this tetra valency, at a time a single carbon atom can show the different combinations with different atoms. Hence, we can conclude like because of tetra valency, carbon can form different varieties of the compounds. And third one is multiple bond formations. So, what is this multiple bond formation? We know between two atoms we can see the presence of either single bond, double bond or triple bond. So, particularly in the case of carbon chains, if you observe here, we can observe the existence of all these three types of bondings like single, double and triple bonds in the same carbon chain only, or sometimes it may form only single bonds. So, like this the multiple bond formations also will change the composition of an organic compound. Hence, we can say that this multiple bond formations also one of the unique properties of the carbon, which is mainly responsible for the formation of millions of compounds in the nature. And finally, if you come for isomerism. So, what is meant by isomerism? Here simply one can describe. So, here simply one can describe the term isomerism like the compounds of same molecular formula with a different structural arrangement and different physical as well as chemical properties. Such type of phenomena we can say as isomerism, and the compounds which are existing with the same molecular formula, but with a different structural arrangement are generally called as isomers. So, here I am giving you two examples. Here one example I have taken with the 5 carbons chain, and the second example also I have taken with the 5 carbons chain. But what slight variation I have shown here is, here in the first case it is represented like a linear or straight chain, but in the second case it is represented like a branched chain. One carbon I have removed from the terminal and I have added at the second carbon, so that the branched chain can be obtained. So, like this, if I take the molecular formula of these two compounds, the molecular formula will be same, but when it comes to the physical and chemical properties, they will show some variation in the physical and chemical properties. So, like this, all these 4 important properties, unique properties of carbon we have to consider, and these are responsible for the formation of millions of compounds in the nature.